Hello, geometry students. Welcome to the second unit of our class. This is kind of the hellish one where we have to talk about proofs and proving things to be true and doing it in a logical and a rigorous way. We'll get to that later. Today's lesson is just about these kind of statements, conditional statements and conjectures. So a couple definitions. One is just this one. A conjecture is an unproven statement. So something that you might notice like a pattern or something, and the conjecture is like a guess about the pattern. It's sometimes hard to prove conjectures, particularly ones in geometry or something, because in order to show that something is true, you have to show that it's true for every possible case. We'll see what that means in a minute. That's quite difficult to do, but it's much easier to show that something is false, because if I find one instance where it's false, I can say that the whole conjecture is false. So we'll talk about these later. And the way that you say that it's false is that one case that you find that where it's wrong is called a counterexample, a specific, it's like just an example of where something, it's an example of where the conjecture is not true. So if I said something like all numbers divisible by 3 are also divisible by 9. Well, that's true for 9. Like 9 divided by 9 is 1, and 9 divided by 3 is 3. So 9 is divisible by both. And 18 divided by 9 is 2, and 18 divided by 3 is 6. So 18 is divisible by 9 and 3. So it looks like maybe things are going well, but then maybe I pick a number like 6. 6 is divisible by 3, which is what it says here, but 6 does not divide evenly by 9. It's just 2/3, which is not a whole number. So not every number divisible by 3 is divisible by 9. Like 9 works and 18 works, but 6 does not work. So this would be a counterexample to the statement all numbers divisible by 3 are also divisible by 9. So we'll see more of those in a minute. So here's an example. If the product of two numbers is positive, then the numbers are both positive. So product means multiply. So if I multiply two numbers that are, so like 2 times 3 is 6. So that's positive. And both the numbers are positive. So that one works. I could do like 7 times 11. That's 77. This is positive, and they're both positive, so that works. But to find a counterexample, I got to find one where I multiply two numbers and get a positive, but the numbers are not both positive. You can do that by doing something like -2 times -3. That's positive 6. So the product of these two numbers is positive, but the numbers are both negative, which is not what this says. So this is like a X. This would be called a counterexample. It's a place where this is called the hypothesis. We'll talk about that in a minute. The first part is true, but the second part is false. Here's another one. The square of a number is always bigger than the original number. So let's take a number. Let's take a number 2 and square it. We get 4. Is that bigger? Yeah, that's bigger than, so 4 is bigger than 2, so that one works. About 10 squared. That's 100. That works. So the negatives seem to give us a problem before. Why don't we try a negative? If I square -2, I get 4. Well, that's also bigger than -2, so that one works. What about like -1? -1 squared is 1. That's bigger than -1, so that works. So far I haven't proved or disproven anything. I'm kind of exploring. I'm kind of guessing some numbers and seeing if it works. And maybe, what if I tried this number? 1/2 squared. Well, that's 1/2 times 1/2, which is equal to 1/4. Is this bigger than 1/2? No, it is not. 1/4 is less than 1/2, so this one doesn't work. This would be a counterexample to this, because it says the square of a number, 1/2, is always bigger, but this number was smaller than the original, so this is a counterexample. Another one is 1. 1 squared is equal to 1. And these numbers, 1 is not bigger than 1, it's equal, so this one doesn't work either. Basically, positive fractions between 0 and 1 don't work, and 1 doesn't work, but anything else will work. So these are called counter examples. These are also, these two down here are also counter examples. So that's what a conjecture, these are called conjectures. If the product of two numbers is positive, then the numbers are both positive. That's a conjecture. It's like a guess you might make, and then you can kind of see if it's true or not. In this case, it's not true because a conjecture has to be always true for it to be true. That's kind of an important point to make. The square of a number is always bigger than the original. Well, that's clearly false because I gave you two examples where the square of a number, I squared 1/2 and I got a smaller number. Here I squared 1 and I got 1, which is not smaller, but it's also not bigger, which is what this says. So these are called counter examples. I will, on assessments, quizzes, and tests, be asking you to find me counter examples to statements. So we're going to talk a lot about these if-then statements. If-then statements are also known as conditional statements. They join two statements together. So here's one that we looked at earlier, or we didn't, but here's an if-then statement. If a number is even, then the number is divisible by 2. That's why we call these if-then statements. These two things, if, then, and conditional, have kind of the same meaning. Close enough for us. So if you see if a number is even, then the number is divisible by 2. This is called conditional because there's a condition. The condition is that the number has to be even, and then the claim is that it's divisible by 2. This is actually true. It's a definition. Numbers divisible by 2 are by definition even. So like this is true for all numbers. Just because it's what, for a number to be even, it must be divisible by 2. That's what it means for a number to be even. And we often refer to these. We talk about a hypothesis and a conclusion. The hypothesis is the first part. If hypothesis, then conclusion. If P, then Q. The reason we just use P's and Q's is because you can use what's called symbolic logic, where it doesn't actually matter what the statements are, and we can tell things about the truth or non-truth of them. But for this example, a number is even would be the hypothesis. Not the if part, just a number is even. This is the hypothesis, the thing I'm outlining in red. The thing I'm outlining in green here, the number is divisible by 2, is called the conclusion of the statement. The conclusion right here in green. And again, notice that the word then is not a part of the conclusion, though it always precedes it. So the hypothesis of this statement is a number is even. The conclusion is the number is divisible by 2. We connect those with the words if and the word then. It kind of makes it just more Englishy. And so we often say the basic form of these is if P, where P is some statement, then Q, where Q is some other statement. And then you can ask yourself questions about whether or not this is true. If you can find a counterexample, you know it's false, things like that. So there are kind of, this sometimes shows up in more than, it doesn't always show up in this if P then Q form. Sometimes people say P implies Q. It means like that this condition, this precondition implies whatever the postcondition is. And then there's another way, P only if Q, and that's like this is a precondition for this to be happening. So if then is the most common one and P implies is pretty common. You don't see this one very often. Like I said above, this little thing in this blue box, if, then, implies, only if, like these extra, these like kind of English words here are not part of the hypothesis or the conclusion. The hypothesis here is it is snowing, and the conclusion is it is cold. It is snowing, it is cold. It is snowing, it is cold. The if and the then and the implies, all that stuff are not part of either the hypothesis or the conclusion. So it says write the other two forms. So here's the if then form they gave us, and it says if two lines are parallel, then they never intersect. So they gave me this first one, if P then Q. The second form is P implies Q. So this is saying two lines being parallel implies that they never intersect. Never intersect. Intersect. So I added a couple of like Englishy words in here. I added being because it feels better than two lines are parallel implies that. I don't know. I kind of like the word being better there than the word are. And then they never intersect is right here. I added the word that. You probably didn't have to have that word there, but I kind of like having it there. It feels more like an actual English sentence than it does if you don't have it there. And I don't know why I underlined these in green when I did them in blue above. Am I doing blue again? So what we've done here is we've just taken this statement and we've rewritten it with the word implies in between them instead of if and then. Then you can say two lines are parallel only if they never intersect. That'd be the third way, the only if way. Two lines are parallel only if they never intersect. And again, here's the hypothesis, here's the conclusion. So this is just the beginning of our kind of logical trip into proving things to be true or false. So we have this other, so that you have a statement, an if then. You have an if P then Q. That's like a generic conditional statement. I don't really care what P and Q are. I just know that it's if P then Q. To make what's called the converse of this statement is statement A. The converse of statement A is formed by switching the hypothesis and the conclusion. You get a converse of a statement by switching the hypothesis and the conclusion. So you switch them. You don't have to do anything else. You just switch them. The converse of the statement if P then Q is if Q then P. This is called the converse of this original statement. Just switch the hypothesis and the conclusion. For example, the converse of the statement, if hypothesis, a number is even, then conclusion, the number is divisible by 2. You get the converse just by switching these two. And you just say, if a number is divisible by 2, then the number is even. Why does that happen? So I took the blue statement, which was the original hypothesis, and I made it a conclusion. And I took the conclusion from the first one. I made it the hypothesis. I just switched the blue and the red statements. This is now the converse. If this is the original statement, this is the converse. And like we said before, it says many true statements have false converses. That's true. This one, it happens to not be true. This statement is true. If number is even, it's divisible by 2. That is 100% true. And the reverse is also true. Number is divisible by 2, then it's even. And that's because this statement is called it's called biconditional. We'll talk about that in a minute, but it's a definition. And those are always true going both directions. So we'll do a couple of examples here. If points are coplanar, then they lie in the same plane. So that, again, we have our hypothesis and our conclusion. And to write the converse, you would just switch those. If points lie in the same plane, then they are coplanar. So again, I took what was the original hypothesis, points are coplanar, and I made it the conclusion, took the original conclusion, I made it the hypothesis. You can see I like switched the word points and they because this they here doesn't make any sense really at the beginning. You want to identify the thing. I can't use a pronoun to identify something later in the sentence. It's a little weird. I can do the same thing with this one. If this angle, whatever, measures 110 degrees, then it must be obtuse. So I would say if angle X is obtuse, then the measure of angle X is 110 degrees. 110 degrees. So again, I took the original hypothesis, I made the conclusion. I took the original conclusion, made it the hypothesis. So this one, number one, is always true. It's true both directions because this is a definition. The definition of coplanar means lying in the same plane, so it doesn't matter which order I put these in. But this one doesn't work. I can come up with a lot of counterexamples. If an angle is obtuse, then it measures 110 degrees. I don't know. What if the measure of angle X was 95? Well, then it's obtuse, but it does not measure 110. So this is one where the original statement is true. This is true. Every 110 degree angle is obtuse. Remember, obtuse just means bigger than 90, more than 90. So it's absolutely 100% always true that any angle that measures 110 degrees is obtuse. So this statement is true. But this statement, if an angle is obtuse and it measures 110, that's false. There's a lot of angles that are obtuse that do not measure 110. As a matter of fact, the only obtuse angles that measure 110 are the ones that measure 110. So I've proven this statement false. This is my counter example. Basically, my counter example, it like satisfies this condition. It satisfies the hypothesis. If an angle is obtuse, this is obtuse, but the conclusion fails. This angle is certainly obtuse, but it does not measure 110. It measures 95. So I've proven that statement, the second statement, false. And earlier where it said many true statements have false converses, here, this is a true statement, but its converse is false. That happens a lot. So I'm going to break this video, but we'll finish this up in the next one.